let's start our next talk. So next speaker is Nick Roy. He's a professor at MIT. His research has a very broad branch, ranging from robotics, machine learning, autonomous systems, planning, and reasoning. He has multiple roles. He directs the Robust Robotics Group at MIT. He's the director of engineering for MIT Quest for Intelligence and founder of Project WIN at Google X. Let's welcome him.
Thank you so much. It's great to follow Danfei, and hopefully what I can do is articulate, I think, so Danfei's laid out a very nice vision for like how in particular we get the data for the language that we want to use inside planning. What I'd like to do is just talk about some ideas that I think follow in that in terms of like what exactly is the right role of language in planning. And I want to begin with just this one idea, which is that we as people reason about the world and the things in it, in particular maps, using some very abstract representations like this. This is from Kitty, but it looks a little bit like a Google map or an Apple map that you might have on your phone. If you contrast that with the kind of maps and representations that we ask our robots to use and often use our robots to build, they look like this. And they're much, much harder to interpret. And this is, in fact, the same environment. This is part of the town in Germany that Kitty is from. But it doesn't look anything like this. It's much harder for us to interpret. And then if you think about the kinds of representations that these kinds of robots use, they look very different again, and they still don't look anything like the kinds of representations that we as people use. And so the question is, if we want our robots to perform more complicated tasks and operate in the real world and interact with us and carry out these complicated plans, how do we actually cross this gap? And so the kind of thing that I'm after is where we can give very high level sort of guidance to our robots. This is an example taken from a demonstration we did at West Point with some Army colleagues, where the actual instruction that we're giving to the robot is kind of implicit in the text of in the language the robot receives. The bag and the shelter and the trash are both suspicious. I need you to secure the area. Well, the robot has to understand what secure means in the context of things being suspicious, and then rendezvous at the tree in the road. We all probably understand what this means, but I think even if we went to like a 4 or 5-year-old who speaks, the appropriate language, they would have trouble interpreting this. So there's a lot going on in how we think about the world, how we represent the world, and how we communicate with each other. And I think that has some interesting implications for how we use language in a planning and decision-making system. One thing that I want to point at, and this is a figure that I've shown a lot in the last few years, is that pretty much every robot that's deployed seriously in the world, not in the lab, but self-driving cars or Mars rovers, et cetera, have an architecture that looks something like this, where there's like a low-level substrate that's operating at a relatively fast duty cycle, that's taking in sensor data, estimating the pose of the robot, something like 100 or 1,000 hertz, and then making control decisions. And then sitting on top of that is a different system at a more abstract representation, running a much slower duty cycle, that's doing things like generating perhaps reference trajectories or sub-goals to be followed. And this architecture works really well, but it raises the question of like, why does this architecture work so well? Why do we have this? And a lot of the time it's because of computational reasons. We can't reason at the lowest level over the kinds of time and length scales that we want our robots to execute plans. You can't solve the self-driving car robotaxi problem of picking people up and taking them to the airport, et cetera, at the level of a motion planning problem. You can't do it. So you need some kind of abstract thing. That's why we have task and motion planning. That's why this workshop exists. But at the same time, the relationship between these two levels, and oftentimes there's more than one level of abstraction, so I've only drawn 2 here, but you can imagine that there's even higher levels of abstraction. It's the relation between these layers of abstraction that often breaks. We've had this, I assume that many of you here have had the experience of like having like, a PDDL planner or something like that sitting on top of your low-level motion execution, and you attempt to do a task and then the thing fails and you realize that you're actually missing a predicate. And so you sit and type a predicate into your domain, and then the robot works again until it doesn't anymore. And then you're sort of doing gradient descent in the space of models by human. Like you're not even using Atom to do your gradient descent, like you're doing it yourself. And so like these hierarchical representations have serious limitations that we have to deal with. It is the case that we've tried to cut our way around the problem in some sense, or try and deal with that issue by using things like LLMs. And the literature is rife, and this workshop has several people talking about using LLMs as planners. And that kind of looks like an architecture like this, where you have like the language specifying something down into like a very low level. And by virtue of things like context windows in the transformer, we actually can reason over long time and length scales surprisingly well. And I want to take a minute and sort of think about we sort of got two ends of a continuum here, which was instantiated a little bit in the debate yesterday. I think the debate was a little bit like a straw man argument, where towards the end of the debate, they actually got into like the real questions of like, how you actually combine the best of both worlds. But it's worth being explicit about what the trade-offs are between the various points on this continuum. On the one hand, the sort of structured optimization where you have a planner doing combinatorial optimization over an explicit model that is usually interpretable. It doesn't have to be. Those models make it easier to provide guarantees, right? So you can put in constraints like don't have collisions and make sure that, this is what the goal location looks like. They're often more data efficient for ways that we'll talk about in a few slides, but they're also a lot more computationally inefficient. That optimization that's happening inside is really painful. And that's, again, why we have this hierarchy. On the other hand, the end-to-end learned policies are typically a lot more flexible. And we know they're more flexible because they're doing more things than we've been able to do using structured optimization. And they're also more computationally efficient, especially if you have like a GPU that allows you to do like, massively parallel things. It's also the case that like, when you do have a failure, you don't have to go and write a new PDDL predicate or something like that. You just collect more data, retrain the thing, and then off you go. And that is usually easier. But they are a lot more data intensive. And so the question then is, how do we get, the best of both worlds? And so I'm going to argue that the hierarchy actually gives us an intermediate point, even with some of the learned models. And we get the best of the both worlds by taking advantage of compositionality, abstraction. And then the hierarchy also gives us correctness as a way to deal with the so-called hallucination problem of large language models. And then it's also going to give us computational efficiency in some interesting ways. So the first thing in compositionality, I'm actually going to talk a little bit about an idea from some folks from my group from actually several years ago that is much less in vogue given the current regime of large language models, but it's worth going back. And it also calls back to my talk, which is that language, I think, is fundamentally about correspondence. So what do I mean by that? So let's imagine we have some very simple language and we have a map. And we have a robot in the map, and the languages go past the elevators through the door down the hallway. Conference room is on your left. How do we compute a plan from this? Well, I had two people that I was working with in my group, just tremendously creative people, Stephanie Talix and Tom Kohler. And they noticed that you could actually formulate the interpretation of this language as a cost minimization problem, where you had a set of actions that you could take through the world in a map, and you wanted to find the lowest cost plan conditioned both on the map and the language. So how do you compute the cost given the language and the map? Well, let's just say that we have some parser that gives us the language, just extracts the first phrase of that language, go past the elevators, and we're at this location in the map, and we have some routes that we might take. And so we might have a cost function that says that, look, here's the trajectory, it's going past something, and we can compute features of that trajectory with respect to the object that's going past. And so we might say that it's going past something, and so that's relatively low cost, but it's going past a fridge, and that's not the elevators, that's relatively high cost. And so we would want the cost function to tell us that was a not very low cost trajectory. This trajectory here is not going past anything, and the thing it's not going past isn't the elevators. This would be relatively high cost. Here's a trajectory that is going past something, and the thing it's going past is the elevators. And so this would be the lowest cost, presumably, trajectory in the environment. And so it's not, so this, you can't, Steph, hang on a second, go backwards. Stephanie and Tom showed that you could actually learn a cost function for these little snippets of language and actually do simple things like follow navigation instructions in the environment. But the problem is we wanted to be able to do more general planning problems, manipulation, et cetera. And it wasn't obvious how to turn the problem statement given some arbitrary language and a set of actions in a map into a more general system for understanding natural language. And again, this is long enough ago. This really predates foundation models. It predates BERT. It certainly predates OpenAI, et cetera. And so data was expensive, and computation was expensive. But what they noticed is that you could actually factor all of the language into essentially a series of correspondence problems where you could write the correspondence as the likelihood that the stuff in the world in the map matched the language. And so you could learn individual correspondences for, let's say, a trajectory in the world going past an object in the elevator. You could learn the correspondences of a trajectory in the world going past something. And this is what I mean when I say language is often best thought of as a correspondence between human model, what you want the robot to do, and the robot model. And what was really nice about this is the language, basically we had a series of tiny little models that we could learn. And, again, pre-large language models, so we're explicitly learning probabilities, and you wouldn't need to do it this way anymore. What was nice is that we could learn the individual components, and then we could stitch them together according to the syntactic structure of the language. And so going past the elevators basically gave us a graphical model for like the correspondence of going past and a specific landmark. And so you had a cost function for going past something, or likelihood, and the likelihood of the thing you went past is the elevator. Stitch those together, do a joint optimization, and you got the likelihood that this trajectory was matched what the human intended. And I'm not going to spend a whole lot more time on this, but we could do things like put the tire pallet on the truck. And we had trained this on an indoor robot, and we were able to then go outside with this robot forklift, and it knew about tire pallets, but that was the only extra thing that we needed to train it on. And then it could follow relatively complicated instructions. And so this worked really well in terms of giving us a way, using language and the structure of language as a way to get at compositionality that drove down our data costs and our computation costs. But it did more things for us than that. Another thing that it gave us is the ability to deal with abstraction in the language. So what do I mean by this? Is that, a lot of our language models don't do well with abstract concepts like picking up the first block in the row of blocks. They're doing better with concepts like nearest, so those large language models have really struggled with spatial relations. And there's lots of evidence in the literature that these large language models are struggling with things like counting. So how do we use our compositional models, explicit model, in order to get at these abstract concepts like counting? So we can reason about large sets of objects by noticing that not just the syntactic structure of the language, but the semantic structure of the language gives us the ability to grow our graph even further. I mean, it's not clear what gets grounded in a palette in a row of 5, but if you know that you're grounding to 5 of something, you can instantiate 5 variables in the world that you're all going to ground to in the row of. And so all of a sudden, we could get. I'm going to skip over that bit about how we ground this, but all of a sudden we could, by basically taking advantage of the syntactic structure of the language and the semantic structure of the language, we could instantiate an underlying model for what was in the world that makes it easy for us to reason about these abstract concepts like counting and rows of things and spatial relations in a way that's very, very hard if you're doing the next token prediction that large language models do. And again, what we're doing is we're using language not to generate the plan explicitly, but to use language to form a correspondence between the human model and the robot model. And so really what we're doing here is using language to feed into that symbolic model additional correspondence variables that inform the planner. So skipping ahead a few years, I started working with Chu Fan and her group, who had been doing a lot of work in formal methods and plan synthesis, again, models. And the question that Chu and I had both arrived at independently, and so we joined forces, is like, well, can we use LLMs to ground into the kinds of models that allow plan synthesis and formal specification very computationally efficiently? And we are by no means the only person to do this. I put a few representative citations down here. If you're not on the list, apologies, like it would have made the slide very busy. We know that there's more people out there, including work at ICRA in one of the last sessions at the end of the day yesterday, which was pretty interesting. But it's worth asking the question of, like, again, what is planning good at and what are LLMs good at? One thing that we know that planning is really good at is it's good at dealing with the interaction between different actions. So planning becomes really important when choosing an action badly early on in your plan sequence locks you out of doing something later on. My favorite example of this is that an LLM will tell you that if you need to put the milk away in the fridge and you see the milk sitting on the countertop, the first thing you should do is pick up the milk. Then you go to the fridge and then open the fridge, etc. That does not work in my house. It does not work at all in my house. And my kids are a living instantiation of how they're not good planners. The reason it doesn't work in my house is because my fridge is always packed to the gills because I have 3 teenagers living in my house. And so if you pick up the milk and try to put it in the fridge, there's no room. So the first thing you do to put the milk away is you open the fridge and notice that there's no room, do sort of the grocery equivalent of Tetris in order to find a slot that the milk fits in, and only then do you pick up the milk. But it's that interaction between the milk in your hand and the objects in the fridge that is why we have to plan and what LLMs are really not great at. So on the flip side, planning really requires a good model. Like it's very, like our planners fail when the models aren't accurate. LLMs, on the other hand, are very good at dealing with the kind of approximate omniscience. And by the way, this slide here is shamelessly stolen from Rao's ICAPS 23 tutorial, which if you haven't read, I highly recommend it. It's really, really excellent. So LLMs are really good at when the model is not accurate because they can basically backfill the approximation errors with background knowledge from having read all the things. On the other hand, planning is really good at the kind of combinatorial optimization where like an action chosen badly early on is really going to cause problems for you. So, and the other thing, of course, is that LLMs can accept any planning problem and almost any formalism that they've seen before, whereas planners are really locked into a particular formalism, but they give guarantees. And so again, this gets set to like these two ends of this continuum that I talked about earlier. And we also know that LLM so much the syntax of how you present the problem to them, but the semantics of how you present the problem to them. So this again is taken from not just Rao's tutorial, but a paper with him and his students that showed that, yeah, you can get an LLM to plan, but if you rewrite the language that you gave the problem to the planner, it's going to not know what to do. And so they showed that like you basically make GPT-4 fail arbitrarily quickly by basically like changing the semantics of the domain without actually changing the instructions. And again, this is Rao's work. And then he went on to say in his tutorial exactly what makes sense for LLMs inside the planning context. So you constructing the world model, like actually that model you're going to run planning on, and we're going to talk about that in a second. Using the LLMs as a heuristic to guide the planner. And then he went on to say there's a couple of places where using LLMs in the planning loop really works. He characterized it as the least ambitious way to use LLMs as plan generation is to just have them give the goal. And then he went on to cite some work by Peter Stone and me and Choo Choo. It's just like, okay, so Rao's called out the fact that we're doing something well and also said it's the least ambitious thing imaginable. So fair enough. But what is nice is that if you use the LLM to instantiate the model and also the goal, then you can get at correctness. And so this is something that Choo Choo and her students and our postdoc Jake Arkin have been exploring. And many people have been looking at this as well. Is can you use the LLM as guidance into a TAMP planner? And one of the things that I want to call out here that I think that we've done nicely is that it's not just like a one-shot LLM into the planner, but the planner actually provides a feedback signal as well, which is super useful. So the way that we've approached this is we use the LLM and some prior knowledge of the environment. So we have to have a map still. And we can instantiate use the LLM to instantiate a initial specification. In this case, we're using STL. And then we can use that STL specification in order to actually synthesize a plan. And then what we do is we use a TAMP planner, given that STL specification, to actually generate that trajectory. But we're not done yet. We can actually take that trajectory and feed it back, or we can verify that plan that we receive and check to see if it's feasible or not. And it's that loop from the language to the specification to the TAMP planner back to the LLM language. We can reprompt the LLM for correction, saying that this plan isn't feasible and why it's infeasible has actually been able to allow us to use the LLM to generate correct specifications. And we basically iterate with the LLM and the planner until we actually get a correct specification, a correct plan. And that's been very satisfying. And notice that we're using syntactic checking early on. We take the initial specification that's derived from the LLM and do syntactic checking to see if it's well-formed STL. If it's not, you iterate back. And then once you have the syntactically correct specification, synthesize the plan, check to see if that's feasible. And if it's not, you iterate back with the LLM. And that's worked very well for us. Once again, language is correspondence. In this case, we're using language to correspond into a specification and then using the TAMP planner to check the specification. And here are some results showing, unsurprisingly, if you just use the LLM as a planner, you're not able to solve nearly as many plans as if we actually use the LLM as the translator and then run an explicit checker. And then here's some results. And again, this is from in collaboration with Choo and her group, and it's been very satisfying to work with her. And I also want to point out, one of the advantages of being Zoom is I can grab a slide from the previous speaker and point out that like this is something very similar to this architecture is very similar to what Dan Fay talked about, and I think I really liked a lot of his message. And the very last thing that I want to talk about, and I think I have about 5 minutes left. Is that right? You still need the actual underlying model of the environment. So where does we know that we need a hierarchy for efficient planning? We still need to make the TAMP planner efficient. And I already talked about how you can't solve the self-driving car problem of picking people up and dropping them off at the level of an underlying motion plan. So we know that we need the hierarchy also in the representation of the world. And so we've been collaborating with Luca Carlone and his student Aaron Ray, and noticing that, or taking advantage of the fact that they have been doing tremendously great work in building hierarchical representations of environments as part of hierarchical mapping. And so if you haven't seen their work in scene graphs, then I really encourage you to look at it. But they are able to build hierarchical representations that go from underlying geometric meshes of the kind you would use a motion planner for to higher level abstractions in terms of places and rooms and buildings and objects inside those environments. And we thought that, great, this will just be a drop in into our hierarchy and we'll be able to solve task and motion planning on this. And we can turn those various concepts in the scene graph into like predicates that we can then give to a task and motion planning problem. The problem, we gave the scene graph to the planner and the planner looked at it and said, what the heck is this? The scene graph that you get is unnecessarily dense. It's incredibly dense. And the problem with that, what that means is that you're very close to trying to, again, solve like a task and motion planning using just a motion planner, that you have too many places in the world, and many of them are irrelevant to the task at hand. So there's a very important need when you're automatically deriving your representation of the world from sensor data, even in using an abstraction like a scene graph, to make sure that the scene graph and the abstraction is aligned with the planning problem. We haven't figured out exactly how to do this with language yet. So language is going to disappear from these last couple of slides of my talk, unfortunately. But one of the things that we have done is we've noticed that we can take advantage of the hierarchy in task and motion planning, and we can factor the scene graph into the symbols that are necessary for different parts of the task problem. For instance, if you're doing mobile manipulation, you can factor the scene graph into the pieces that are necessary for the mobility part and the pieces that are necessary for the manipulation part. And then you could throw away the rest of the scene graph and just plan across that. And so this is an example. This video here shows us taking a plan specified, in this case from PDDL, and then solving this using a planning model derived entirely from the sensor data. We have actually connected the PDDL generation to natural language. I just don't have a result for that here. So we can now specify a plan in natural language, give it to combine it with a model derived from the sensor data, and then give that to a task and motion planner and solve that. And that's pretty cool. And what you see here is the effect of the density of the scene graph on the solution time. And unsurprisingly, the denser the scene graph, the worse the computation time. At some point, though, you actually need the fullness of the scene graph in order to solve this. So we've done some different experiments showing like, complexity of the problem, vary the goal complexity, and show the relationship between the number of PDDL objects needed and their solution time, et cetera. So hopefully I've shown you a few results here that suggest that there may be a way to think about the language with respect to task and motion planning as a correspondence variable, in particular, an observation of the correspondence variable, to enable compositionality, to drive down data complexity, to enable abstraction of the kind that we're seeing LLM struggling with, to give us correctness, and then to give us computational efficiency. Things that I haven't talked about are like, dynamics. What happens when the world changes under you? We got some work going on that. Secondly, I put on this slide that language provides a measurement of the correspondence. What happens when the language is ambiguous or unclear about the correspondence? We don't have an answer to that yet. So I think there's a lot more work to be done in this case. I want to say thanks to the students. Many students and collaborators have been involved with this. Thanks to the sponsors, and thank you all very much.
Thank you. We probably have time for 1 or 2 questions. I have a question. So when I use ChatGPT, if I tell him that it's wrong, it will say what I say. So in the case where you use LLM to check for correctness, do you see similar behavior that if you tell it it's correct, it will say it's correct?
So what we tend to do is we say, this is what you said, and this is infeasible, and here's where the infeasibility is. And then what we see is generally a correction in that case. So you have to prompt it correctly. And you're absolutely right. If you don't get that prompt correct, then it's so our auto TAMP paper basically talks through how you would want to prompt a large language model in order to get the kind of behavior we're talking about. Absolutely. It's a really good point.
Thank you.
Yep.
So, thank you, Jan.
I have one question.
So,
Oh, yeah.
Yes. Hi, Professor Roy. Thanks for sharing your insights. You mentioned, leveraging LLMs as translators between natural language and specification languages. And in our own work, actually, with Stephanie, we've seen great success in that approach. But I have a question about verifiability. How do you verify that the translated formal language matches the user's intention?
So that's a good point. And so we can't verify that level of correctness. What we can verify is A, syntactic correctness, and B, semantic correctness in terms of like if there are additional constraints on the plan. Is the plan feasible as specified? If we completely misinterpret the plan and the instruction is like, go pick somebody up from Logan and they end up driving to